Hey everybody, it's Mr. Woodward. Let's talk about electric fields. So first of all, an electric field is a force field, a region of force that's in the space surrounding anything that's charged, okay? Kind of similar to a gravitational field, except a gravitational field is in the region around any masses. So looking at this description on the left, it says these pictures show charged pieces of metal in oil with silk thread. Okay, so all these kind of lines moving outwards are little pieces of silk. In each picture, do you think the objects are similarly charged or oppositely charged? Okay, so in the first picture, I'm just going to exaggerate these lines a little bit more, or more kind of clearly define them. And you have to imagine that if these charged objects weren't in here, these little pieces of silk thread would just be going kind of in all directions like a bowl of spaghetti. But now they're forming these clear patterns. So what's causing them to form these clear patterns? Well, in the first picture, it looks like the silk is sort of connecting from one of the charged pieces of metal to the other. In picture B, now it looks like the silk is sort of going out, but then almost like not wanting to move towards each other. You can see the silk sort of bending away. Let me get rid of that one. Okay, in this one, we see almost like this attachment between the two. Now these are like metal bars. And in the other one, we have this sort of bending of these silk threads coming out this way, right? So what's going on here? Well, in picture A, in this picture first, this attraction between the two pieces of metal must be because the two metal dots are oppositely charged. So one is positive and one is negative. So I'm just going to sort of, guess and say that maybe this is the positively charged dot and maybe this is the negatively charged dot. And that would explain why their lines are connecting from one to the other. There's clearly an attraction. And that's what the silk lines are trying to outline. In the second picture, though, we see a repulsion. The silk thread lines are not intersecting. They're sort of trying to get away from each other. So either it's because both dots are positively charged or both dots are negatively charged. It could be either. I don't actually know. So I'm just going to pick one. Let's say that they're both negatively charged. And I'll go over here and circle them. Okay, in the third picture, we see more of an attraction, but now it's an attraction between two metal bars. So one of them must be positively charged, while the other one must be negatively charged. So I'm going to fill this one with minuses. And then we get another attraction here in this picture, and again, it must be because one is positively charged, while the other is negatively charged. And I keep picking the wrong green color. There we go. Now, physicists will go one step further and they would say, gosh, wouldn't it be nice if we had a convention for the direction of the electric field? And so they would define the direction of the electric field as always going away from the positively charged thing and towards the negatively charged thing. So if I was to take these lines and turn them into vectors, right, by adding an arrow, then they would look like this. Right, we're going from positive to negative. So I would just add an arrowhead to all of these lines, and my mistake, electric field lines will never cross like that. So we'd have these arrowheads, right, going away from the positively charged thing and towards the negatively charged thing. That's the made-up convention for physicists. So then these would all point inward, right, towards negatively charged things, away from positively charged things. These would all point inward as well. Okay, towards the negative, away from the positive. And then similar here, right? Away from the positive, towards the negative. All right, so that's an introduction to electric fields. Again, it's a force field surrounding anything that's electrically charged. And then here's some practice with more of these kinds of pictures. So I'm going to do like the first two, and then I will invite you to fill out the rest. So starting with number 1, electric field lines begin on positive charges, right? I already mentioned that. And they terminate, meaning they end. Okay, terminate means end. They end on negative charges. The number of lines, and here this is new, the number of lines that emanate from a charge or approach a charge depends upon the strength of that charge. Or better put, the quantity of charge. So something that has a lot of coulombs of charge would have a lot of electric field lines going out of it. At locations where a line meets the surface of a charge, the lines are drawn in a radial direction. Like this, right? Here's the surface of this charge, and where those electric field lines intersect the surface, they're drawn radially. That means outward, like this. The strength of the electric field is blank wherever the lines are close together. That's greatest. So the way that a picture indicates a really strong electric field is by drawing those lines closer together. So for example, here at object C, out here, you've got the lines like pretty far apart from each other. So the electric field is weaker out there, but then in here, the lines are closer to each other, so the electric field is really strong. This gives us an indication that an electric field is an inverse relationship to distance, right? The closer the distance, the stronger the field. As you move outwards away from that charge, the electric field strength weakens. Okay, so we have some objects, looking at here, we have some object A. We don't know if it's positively or negatively charged, but we do see that the lines are going outwards away from that charge. So we could confidently say that must be positively charged, because the convention is that electric field lines go away from positively charged things, and then they go towards negatively charged things. So object B must be negatively charged. And then again, with that same idea, electric field lines go away from positively charged things, so C must be positive, and towards negatively charged things, so D must be negative. Please continue working through this, identifying the strength of the fields, and then identifying in number 4 what the electric field would actually look like. So you're going to draw the field in number 4.